Hey guys, good morning. How was the weekend? Good? Great. So today I will talk about excited states. How to get some insight into the excited states of electronic systems. As you know, density function theory is a ground state theory. So even though many, including myself, literally all of the practitioners, use ground state density functional theory to get some insight into excited states, this is strictly speaking not justified and is bound to quantitative in some cases, quantitative I would say in many cases, and qualitative in some cases errors. So new methods are necessary to simulate excited state properties. And today I will present you the simplest of such methods, that is the time-dependent generalization of density functional theory, called the time-dependent density function. So let me just start with a few statements on the connection between excited states and what is actually measured in the laboratory. So as a theorist or as a modeling scientist, in general you may wish to solve the Schrödinger equation, the time-independent Schrödinger equation, not only for the ground state n equal to 0, which is the scope of ground state density functional theory, but for every or a few excited states. Actually, in the laboratory, what is done, excited states by themselves are never measured. What one measures in the laboratory is the response of the system to some external probe that they be time dependent. For instance, a time dependent electric field, you shine light onto a system and you observe the reflected light, the absorbed light, you name it. You measure how the system responds to some time-dependent perturbation. So all the relevant information about the response of the system to an external perturbation P is embedded in the generalized susceptibility chi that tells you how to linear order, this is a linear susceptibility, how to linear order some property of the system that we nickname the response to some given perturbation. What has this to do with our original problem of calculating excited states? Well, you go to a many-body theory or advanced quantum mechanics textbook, and you look for the general expression for such a susceptibility, and you find out that this susceptibility can be expressed in terms of an infinite sum over all the excited states of some magic products of matrix elements of the two operators that are related by the response, so the matrix element of the perturbation between the ground state and the excited state, the matrix element of the response operator between the ground and the excited state, divided by some energy denominator. So basically, what quantum mechanics textbooks tells you is that in order to calculate such a susceptibility, you have to solve the Schrödinger equation first. So the textbook way is solve the Schrödinger equation first, if you can, and from the ingredient of the Schrödinger equation, that is the eigenvalues that go into the denominator, and the eigenvectors from which you calculate the numerators, you calculate the response function. Actually, the imaginary part of this response function has singularities, well, both the real and the imaginary part. The real part has poles, and the imaginary part has delta spikes in correspondence to excited states. So from the location of the poles of the singularities of the response function, you get information on the response function. So what your colleagues in the laboratory would do, they would measure chi, and from the analytic behavior of chi, from the position of the singularities of the response function, they would get the positions of the excitation energies. From the intensity of each of the peaks, they would get information on the matrix elements, and from the width of the peaks, they would get information on the lifetime of the excited state. What a quantum mechanics student would do is the other way around, is to solve first for the Schrödinger equation and to calculate the response function to compare with the experiment then. But the solution of the Schrödinger equation is a difficult task for the ground state. It is an even more difficult task for the excited state. So if you had access to the susceptibility directly, in one way or the other, without calculating excited states, then without solving the Schrödinger equation, then by the knowledge of the susceptibility, you could get information on the excited states the same way as experimentalists would, right? Suppose that you can calculate this susceptibility with some magic black box that give you this number as a function of omega without solving the Schrödinger equation. Then, by this knowledge, you would not solve the Schrödinger equation, but you would get the same information that your colleagues in the lab would get. So density functional, time-dependent density functional theory is one such way of calculating response functions without solving the Schrödinger equation. And from the knowledge of the response function, we get information on the excited states without solving the Schrödinger equation. So this is the program of the next hour of lecture. Calculating response functions without solving the Schrödinger equation, and from the knowledge of the analytic property of the response function, get information on the excited states. Okay, time-dependent density function theory is based on a theorem established by Runge and Gross in 84. I'll give you in a while the reference. The theorem is a generalization of the Hohenberg and Kohn theorem that establishes a one-to-one correspondence between potentials and densities. So let us, you may remember how we introduced density functional theory. We introduced it by starting from a trivial functional, the function that relates the external potential to the density, that requires implicitly the solution of the Schrödinger of the ground state Schrödinger equation, and then we provided an argument based on convexity and the Legendre transforms and stuff to show that this map from the potential to the density can be inverted. Let us see how this can be done in the time-dependent case. So in the time-dependent case, you have in general a time-dependent Schrödinger equation, which, contrary to the time-independent Schrödinger equation, does not have a unique solution. It has one solution for each initial condition, right? So the wave function as a function of all the coordinates and time would depend on the starting wave function. So given a starting wave function at t equal to 0, you have a well-defined time evolution of the Schrödinger equation. So this time evolution of the Schrödinger equation gives in correspondence to any initial condition, any psi at t equal to 0, gives a well-defined mapping, a well-defined correspondence between the external potential acting on the electrons and the time-dependent density. So this functional is trivial, though very complicated, if not impossible to calculate in practice. That is, you give me a time-dependent external potential acting on the system of interacting electrons. You give me the initial condition, psi of t equal to 0. I would solve for you the time-dependent Schrödinger equation that gives me psi of t, and by calculating the expectation value of the density, the charge density operator over psi of t, I get the time-dependent charge density. Very complicated to do in practice, but very simple and straightforward in principle. In 84, Runge and Hardy-Gross demonstrated the following theorem that I will not give any detail on the demonstration, but just the statement in 2 lines. So for any time-dependent charge density distribution n of r and t, and for any initial condition of the time-dependent Schrödinger equation that are an input of this argument. Of course, this initial condition must be such that the expectation value of the density at t equal to 0 is equal to the starting density. So this pair of functions, the density and the wave function, cannot be totally arbitrary. So they are constrained, they must be constrained by the fact that the initial density is the expectation value of the density operator over the initial wave function. So for any such pair of functions, density and wave function, then there is only one potential that gives that wave function out of the solution of the Schrödinger equation. That is, there are no two different potentials, no potential differing by more than a simple trivial time-dependent constant that give the same density. The demonstration is much more cumbersome than in the time independent case, and much less general. It relies on a number of assumptions, differentiability, the possibility of making Taylor expansion in time of all the quantities that we are concerned with, and I will not give any detail about the demonstration that would take half an hour or 40 minutes by itself to show. But everything is contained in this PRL seminal paper, and many papers have appeared since this paper. It is just one remark. It is not surprising that the demonstration is much more complicated and much less general than in the time-independent case, because in the time-dependent case we saw that the theorem is an almost trivial consequence of the convexity of the Schrödinger functional, of the mapping between the external potential and the energy, much in the same way as the energy is a convex function of the volume in classical thermodynamics. And in a sense, it's almost trivial in the time-independent case. In the time-dependent case, there is no convexity argument that can be used, and there is no thermodynamical analogy that can be used, and so is a kind of the demonstration of the theorem is a kind of tour de force, mathematical tour de force, and the result is, as said, rather less general than in the time-independent case. Still, let us keep the theorem as stated. Let us take as granted the statement of the theorem, and let us remember that under rather general assumptions, the correspondence between time-dependent density and time-dependent external potential that generates this density is invertible. Not only there exists a unique density corresponding to each potential for a given starting wave function, which is trivial, which is a consequence of the Schrödinger theory, but the other way around also holds. That is, for any given density, there exists a unique potential that generates such density. Sure.
See, in usual time-dependent perturbation theory, we actually, after doing the perturbation theory for excited, recover the kind of Fermi-Walden rule, and also recover set of selection rule, which transitions are possible, which are not. If we use this formalism, are we also going to get the allowed transition between excited state automatically?
We will come to this. Selection rules will come out of the properties of the response functions that can be calculated from from time-dependent density function theory. But so they will come out of a linearized version of TD-DFT, which gives access to response functions that are linear properties. But the Runge and Gross theorem by itself is not limited to small perturbations. In principle, it applies to perturbations of any strength. We will use this formalism only in the linear regime. That is, only when the time dependence of the external potential is a small perturbation with respect to a time-independent potential. In that case, selection rules can be established, and we will see. We will comment briefly how. Okay. So, remember that in the time-independent case, what really enables us to apply DFT to real problems is not quite the general statement of the correspondence between density and potential and potentials, but it is the Kohn-Sham construction. It is the Sham construction that allows us to map our many-body problem onto a system of non-interacting electrons that you can treat, although approximately, and which allows us to get quantitative information on the system under investigation. Let us see how the same reasoning, the same conceptual path can be applied in the time-dependent case. Remember, the definition of the non-interacting kinetic energy functional that is essential to write down time-independent Kohn-Sham equations basically stems from the obvious observation that the same theorem, the same Hohenberg and Kohn theorem in the time-independent case, applies equally to interacting as well as non-interacting electrons. So for each given density, you can define an external potential that gives that density in the interacting case, and you can define an external potential that gives that same identical density in the non-interacting case. The potential that gives a given density in the non-interacting case is nothing but the Kohn-Sham potential, out of which we construct all the self-consistent signs. Exactly the same argument applies in the time-dependent case, because the only ingredient of the argument is that for each density there exists a unique potential that gives the density, both in the interacting and in the non-interacting case. So let us write formally. Let us start from a given density, and let us ask ourselves what are the potentials that give this density in the interacting and non-interacting case. So for the regular physical interacting time-dependent Schrödinger equation, and for an auxiliary fictitious non-interacting system, Schrödinger equation for non-interacting electrons, in both cases there exists a well-defined and unique potential that gives the density that we start from. So this allows you, if you want, to define a non-interacting potential that gives, so this scheme can be seen in any possible combination. You can start from the density, and you show that from the density the Runge-Gross theorem states that for this given density you have a potential for interacting and a different potential for non-interacting electrons that gives that density. But you can also reason in any combination of these three ingredients, V, Kohn-Sham, and N. You can start from the physical potential. That is what you actually do, right? We never start in density functional theory from the density. We always start from the external potential. Then, for any given external potential, of course, there exists a unique density generated by the potential, obvious. But for this unique density, there exists a unique external potential for the non-interacting case that gives the same density. As any of these relations is invertible, evidently also the relation between V and VKS is invertible, right? So for any external potential V, there exists only one external potential for non-interacting electrons that gives the same density. Okay? This allows us to define the Kohn-Sham potential the usual way, the stupid Feynman's way of splitting out what we know and naming what we don't know with the flag, with the tag exchange correlation. So we start from the physical external potential, and we say that the Kohn-Sham potential, that is by definition the external potential that gives the same density for non-interacting electrons, is given to the external potential plus the electrostatic potential generated by the density. This is just a definition, just to split out the classical contribution, the electrostatic classical contribution to the potential, plus what we don't know how to calculate otherwise. And we name it the exchange correlation potential, that is a functional of the density. Or if you want, it is a functional of the external potential itself. Okay? Of course, if little is known about the exchange correlation potential in the static case, even less is known in the dynamical case. The dynamical case, it is really a mess, because this functional dependent is not instantaneous. In principle, the exchange correlation potential at time t depends on the density at all the prior times. There is no reason in terms of the Runge-Gross theorem, there is no reason why this dependence has to be local in time. In practice, most of the current approximations to time-dependent density functional theory assume that the exchange correlation potential only depends on the density at the same time at which it is calculated. This approximation is called the adiabatic approximation. Of course, there are a few constraints that you may easily guess on the dependence of the exchange correlation potential on the time dependence of the density. Of course, the exchange correlation potential now cannot depend on the density tomorrow, right? Because causality has to hold. So this dependence has to obey at least causality. So this dependence can only be on the past of the density. There are a few such constraints that have to be taken into account, but very little is known on this functional dependence, and all we can do is to rely on some kind of so-called adiabatic approximations. By adiabatic approximation, what people mean is the locality in time. That is the fact that the exchange correlation potential at time t only depends on the density at the same time. This is what in the literature is called the adiabatic approximation. That has nothing to do with Born-Oppenheimer. Pay attention. It has the same name, but it has a totally different physical meaning. Confusing to some extent, but that's the way it is.
Can this density, so when perturb the system, can this density have occasionally singularity involved in the system? Local fluctuation in the density under the perturbation may be very high. If that happens for some reason, does it happen? I don't know.
In time?
Yes. Because in statistical system it happens. Near the phase transition and so on.
Something similar here occurs at resonance, but then the singularity is in frequency, not in time. When we will, of course, near a resonance, the susceptibility diverges, and you have a very large response for a very small perturbation. I think we may even conceive of singularities in time, but I think this would not correspond to any simple property of the response function. Actually, I think that in order to have very large responses in time, you have to go to higher order response. In the linear regime, the response in time is rather boring. It's a convolution, as we will see. Okay, this definition of a Kohn-Sham time-dependent potential, that is a an external potential that gives the same density as the interacting density, but for a non-interacting Schrödinger equation, allows us to write the Schrödinger equation for the fictitious system, that is the system of non-interacting electrons, in terms of one-electron orbitals. Because if the electrons do not interact, and if the initial condition, the many-body wave function at t equal to 0, is a Slater determinant of orbitals, then the time evolution of that Slater determinant under the action of a non-interacting Hamiltonian will be a time-dependent Slater determinant. So, for non-interacting electrons and initial condition of a determinant type, you can write time-dependent Schrödinger equation for the one-particle orbitals, for molecular orbitals. So you don't have here the electron-electron interaction vanishes, and each orbital evolves independently of the other under the action of the external potential that we nicknamed Kohn-Sham potential. As we saw, the Kohn-Sham potential by definition is the external potential plus Hartree plus exchange and correlation. For non-interacting electrons, the density is nothing but the sum of the square moduli of the molecular orbitals. From this density, you calculate the Kohn-Sham potential. From the Kohn-Sham potential, you advance the Schrödinger equation step by step. It's a first-order equation, so it can be solved numerically step by step. And you can close the circle, close the cycle, much in the same way as you would do for a self-consistent cycle in the time-independent case. In the time-independent case, what you look for is a better approximation to a static solution. Here there is no static solution, and there is no better approximation to it. You have just to follow in time the time evolution, but the conceptual ingredients and the practical ingredients that are necessary to solve this time-dependent Schrödinger equation are basically the same as in the time-independent case. That is, you start from a density, you advance from the density, you calculate the Kohn-Sham potential that is a functional of the density. From the Kohn-Sham potential, you advance by a time step the time-dependent Schrödinger equation. With this, you calculate the orbitals at a later time step. From the orbitals at a later time step, you calculate the density at that later time step. From that density, you update the potential, and you continue to solve the time-dependent Schrödinger equation. So the time-dependent Kohn-Sham Schrödinger equation is all is needed to calculate response functions within time-dependent density functional theory. But for reasons of algebraic simplicity, it is better to work rather than with the Schrödinger equation, with that is an equation for the molecular orbitals, to work with the Liouville equation, that is a totally equivalent equation for the density matrix. Let me just review a few concepts for you and show you how this Liouville equation can be derived from the Schrödinger equation. Let us start from the Kohn-Sham time-dependent Schrödinger equation that I write formally in this compact operator form. basically you have that the time derivative of each molecular orbital is equal to the product of the Kohn-Sham Hamiltonian at the given time times the orbital at that same time. Now define the density matrix as the projector over all the occupied states. So you have a number of occupied states that is equal to the number of electrons, and you define the density matrix as the projector over the manifold spanned by the occupied electrons. Of course, if this sum would extend up to infinity, up to over all the states in the Hilbert space of your molecular system, that would be the identity. But the fact that you limit that sum to only the occupied states turns the resolution of the identity into the identity restricted over the manifold of occupied states, that is the projector over the occupied manifold. Now let us try to calculate the time derivative of rho. It's very simple. You have just to apply the rule for the derivative of product. So of products, this rho is the sum of products of cats and bra. So rho dot is equal to the sum of the derivative of the cat and of the bra. When you derive the cat, this brings in Hamiltonian on the left, right? When you differentiate this cat here, you get a Hamiltonian on the left. When you differentiate this term, you get a Hamiltonian on the right. By passing the Hamiltonian from the left to the right, you have to account for this I factor here that changes the sign when you take the Hermitian conjugate of an operator. So these two terms, the one with the Hamiltonian on the left and the one with the Hamiltonian on the right, have an opposite sign. You combine the two and you get the commutator. This is a simple, formally very simple equation for the density matrix that says that I times the time derivative of the density matrix is equal to the commutator between the Hamiltonian and the density matrix. This is totally, completely equivalent to the Schrödinger equation we started from, and it is very analogous to the Liouville equation for the phase space density in classical mechanics. That's why it is called the quantum Liouville equation, and the operator that acting on density matrix that is defined by the commutator of the Hamiltonian with the density matrix is called the Liouvillean superoperator. It is called the superoperator because it is an operator acting on density matrices that are by themselves operators. So it is an operator acting on operators, and in the chemistry, in the quantum chemistry literature, it is called a superoperator, the Liouvillean superoperator. The main reason why the Liouville equation is more convenient than the Schrödinger equation, to which it is strictly equivalent, is that the Schrödinger equation is defined up to a time-dependent phase, right? You can multiply each time-dependent orbital by an arbitrary time-dependent phase, and you will get the same physical solution. These phases are arbitrary, but they are annoying. You have to take care of them, and you have to take care that the results that you get are, as they have to be, independent of the phases. For density matrices, instead, there are no phases that could ever bother us, because an arbitrary phase on the cat would cancel at the same arbitrary phase on the bra, and so the quantum Liouville equation is invariant with respect to gauge transformations with phase transformation of the molecular orbitals. Two very important properties of the density matrix that will be used in the next few slides are that the density matrix is idempotent. By idempotent, one means that the square of the matrix, the square of the operator is equal to the operator itself. This is a statement basically that this operator is a projector, and the square of a projector is equal to the projector. Or stated differently, it has eigenvalues that are only 0 or 1, which are the two real numbers whose square is equal to the number itself. And the expectation value of any observable can be calculated as the trace of the product of rho times the operator you want to measure, the observable you want to measure. This is a compact way of stating that the expectation value of A is equal to the sum over all the occupied states of the expectation value of A calculated over individual molecular orbitals, right? So this is basically, this trace is the sum over V of phi V A phi V. So this is the general framework we want to use, but our final purpose is to calculate response functions, susceptibilities, because it is from the knowledge of the singularities of the response functions that we can calculate, we can locate excited states and calculate properties of excited states. So in linear response theory, what you have a potential acting on your system that you split into an unperturbed part V naught and a perturbation V prime, and you want to calculate what is the density corresponding to that potential, that again one splits into an unperturbed part N naught, that is the density generated by V naught, plus N prime, that is the linear density response to V prime. By definition, we can define a generalized susceptibility chi as the linear operator that relates N prime to V prime. This equation, as complicated as it may seem, is nothing but a definition of linearity. So the most general linear relation between two functions N prime and V prime is given by an integral kernel, an integral transform, and we call the kernel of that transform, we call the susceptibility. Notice two important features of this expression. The first is that this susceptibility depends on time only through the difference between the time argument of the density, that is of the response, and of the perturbation. Why is it so? This is simply time translation invariance. This states, this equation, that this statement that chi depends only on time differences is simply the statement that the response that I get now to a perturbation that I introduced 1 hour ago would be the same as the response that I would obtain tomorrow to a perturbation that I could apply in 23 hours, right? If I have the unperturbed system that is at equilibrium and time independent. So if I make an experiment now, or I make the same experiment tomorrow, I have to get the same result. This is formally stated by the fact that response functions only depend on differences of times. So the appearance of a difference is a formal statement of time translation invariance. The fact that the time integral extends from the far past, from minus infinity, to the present, and not to the future. So this integral is from the far past to now, and not from the far past to the far future. This is a statement of causality. This indicates that the response of the system now does not depend on any perturbation that I may apply tomorrow. Okay, very important. So these are the two physical requirements that are embodied in this formula, that is time translation invariance and causality. But other than these two general physical requirements, this is nothing but the statement of a linear response. If you are mathematically oriented and if you have metabolized the concept of functional derivative, you will recognize that chi is nothing but the functional derivative of n with respect to v. So the susceptibility is by definition the functional derivative of the time-dependent density with respect to the time-dependent potential. In Kohn-Sham theory, we saw that the Kohn-Sham potential is equal to the external potential plus Hartree plus exchange and correlation. Here I should have said, sorry, here there is a mistake. This label here is not Ks, this is Xc. So the perturbation to the Kohn-Sham potential is equal to the perturbation to the external potential plus the linear response of the Hartree potential, but the linear response of the Hartree potential is simply the convolution of the Coulomb kernel 1 over r minus r prime times the density plus the functional derivative of the exchange correlation potential with respect to the density. Again, this is not Ks, this is Xc, convoluted with the external, with the time-dependent density. Yet another mistake. Sorry, I will correct the mistakes in the notes. This is n prime of r prime and t prime. So two errors in this formula. This label is exchange and correlation, and here there is a missing t prime argument in the density.
So there will be also an integral over t prime.
The three errors. Very good. Okay. There is a missing integral on time. Sorry about this. So we saw that for any given external density, we can formally define two different potential giving rising to it, corresponding to two different physical systems, two different systems. The physical one that is characterized by the V potential, and the fake one electron one that is characterized by the Kohn-Sham potential. For non-interacting electrons, that is for the Kohn-Sham potential, the susceptibility can be easily calculated in terms of one electron excitations. What you have to do, you take the general formula that I gave in the first slide that gives susceptibilities in terms of excited states, of general many-body excited state. You restrict yourself to systems of non-interacting electrons, where excited states are basically given by determinants where you excite an electron from an occupied state to a virtual one. You apply this and you end up with this cumbersome but straightforward formula that gives you the susceptibility for non-interacting electrons. So this is a formula that only applies when the electron-electron interaction vanishes, so it applies to the cone-sham system and not to the physical system, in terms of conduction states and valence states. This, as complicated as it may seem, this is nothing but the generalization to inhomogeneous systems of the Linder formula that you find in any elementary solid-state textbook. Okay? This is the Linhard dielectric function generalized to inhomogeneous systems. But now we are not interested in the calculation of the susceptibility of systems of non-interacting electrons. So we are not interested in the, well, before I proceed, let me just make a remark that I passed from a formulation in time to a formulation in frequency. What allows me to do so is the fact that this formula that relates the density to the density response to the potential perturbation is a convolution in time. Given that it is a convolution in time, it is a product in frequency, so that the relevant quantity to calculate is the Fourier transform with respect to time of this kind. And the formula given here is the formula for the Fourier transform of chi in the case of non-interacting electrons. It is more convenient to work in frequencies rather than in time for two reasons. First, because convolutions become products, which are simpler, and also because we have explicit formulas for the susceptibility in the frequency domains, whereas we don't have equivalent explicit formulas for the time domain. Actually, for having formulas for the time domain, we start from the frequency domain and we make the Fourier transform. So we are interested not in the analytic properties of chi naught of the susceptibility of systems of non-interacting electrons. We are interested in the analytic properties of chi, that is the susceptibility of the physical system of interacting electrons. How to pass from chi naught that we can calculate explicitly, it is cumbersome but doable, to chi. Well, let us first write two identities that are just two definitions. The same n prime, the same density response, can be seen as the response of the system to the physical perturbation v prime, and in this case the response function is chi. But you can also see the same n prime as the response of the cone-sham system to the cone-sham perturbation. We saw that this is an application of just the cone-sham construct. The same density can be seen as originated by the cone-sham potential in the non-interacting case, or the physical potential in the interacting one, in the physical one. By the same token, the same density response can be seen as the response of the physical system to the physical perturbation, or as the response of the non-interacting system to the cone-sham perturbation. Just a simple application of the concept of the cone-sham construct. Now, let us see. I want to calculate chi. I know chi naught. What I need to close the loop, to close the circle, is a relation between v prime and v prime ks. But the relation between V prime and V prime Ks is stated here, but for the fact that here on the right hand side I have N prime and not V prime. So let us play a little bit of algebra, and here let us replace in this equation, let us replace V prime con sham by this definition that implies the knowledge of N prime, and where I have introduced this kappa integral kernel that is the sum of the electron-electron interaction plus this so-called exchange correlation kernel that is the functional derivative of the exchange correlation potential with respect to the density. Let me indicate this formally as a kappa kernel. But then this N prime, I can use this definition of chi. So in place of N prime, I can substitute chi V prime. So I have here chi naught V prime, this term here, plus chi naught kappa, and V prime, and N prime, but N prime is chi V prime, right? Now let us look at this identity. You have that chi V prime is equal to chi naught V prime plus chi naught kappa chi V prime. And this has to hold for any V prime. So this has to be an identity not for density responses, it has to be an identity for the kernels. So we arrive at the conclusion that chi is equal to chi naught plus chi naught kappa chi. This is a linear equation for chi that can be solved once one knows chi naught. We will see a little bit more in detail in the next 2 slides how this works in practice.
When we go from the time domain to the frequency domain, how this homolumous state picked up means balance and conduction, I think so, right?
Sorry?
Epsilon B and epsilon C stands for balance and conduction energy, right?
Here, yes.
Homolumo, right?
Yes.
So when you go from time domain to frequency domain, how these two balance and conduction states are picked up in the calculation?
No, these are the unperturbed. These are conduction and valence states of the unperturbed system. There is no time and no difference and no frequency dependence. These phi and epsilon are calculated once for all for the unperturbed system. In fact, the response functions are exact properties of the unperturbed system. They give information on the excited states, but they are properties of the ground state of the unperturbed system. So let us specialize. We have been very general. We are talked about general susceptibilities that are the response of the most general operator R to the most general perturbation P. Let us restrict to something more practical, and let us specialize to polarizabilities. What is the polarizability? The polarizability is the dipole response to an incoming homogeneous electric field, right? So you shine light onto a molecule when the wavelength of the molecule is much larger than the molecular dimensions,